This is the second lecture of the fourth week, and we're going to discuss the measures of fit, focusing on adjusted R-square. We're going to start off with talking about SCR and RMSE. SCR, which stands for standard error of regression, and RMSE, which stands for root mean squared error, has the same meaning as in simple linear regression. They both mean that it measures the spread of the observed y's around the regression line. In other words, it measures the standard deviation of y around the regression line. The only difference between the simple linear regression model, SCR and simple linear regression model, and SCR and multiple regression model is the fact that you're dividing by n minus k minus 1. In simple linear regression model, we divide it by n minus 2. And that's because k represents the number of regressors. So in simple linear regression model, k is actually equal to 1 because we only have one independent variable. If you have two independent variables, k would equal 2. So you would have to divide by n minus 3. When the sample size is really large, meaning when n becomes really large, then SCR and RMSE becomes similar or almost the same. And that's because when you're dividing it by n minus k minus 1, or whether you're dividing it by just n, when the sample size becomes really, really large, it doesn't really make a difference. The reason why we do this, why we divide by n minus k minus 1 instead of n, it's because we want to make degrees of freedom adjustment for the bias that is introduced by estimating the coefficients. And also the reason why we include or why we subtract 1 in addition to number of regressor is because we're estimating the coefficients of slope as well as the intercept. The definition or the meaning of R-square in multiple linear regression is the same as that in simple linear regression. The formula is also the same, 1 minus SSR over TSS, or ESS over explained sum of squares over total sum of squares. So whenever you add the variable or add another regressor independent variable, R-square always increases. And this is because by design, OLS minimizes the sum of squared errors, or SSR. So whenever you add a variable, SSR would stay the same or it decreases. And if SSR decreases, SSR over TSS also decreases. And since the R-square formula is subtracting this SSR over TSS from 1, if whatever you're subtracting is decreases, then R-square actually increases. So in short, whenever you add a regressor, R-square would increase. The problem is that this would incentivize you to add as many regressors as possible, since R-square keeps increasing every time you add a regressor. But the downside of this is that you're gonna find some of the regressors that are significant even though they're meaningless, just by chance. So in multiple linear regression model, we have something called adjusted R-square. And adjusted R-square corrects for this incentive to add as many variables as possible by penalizing you for including another regressor. So if you look at the formula for adjusted R-square, it looks pretty much the same as regular R-square, except for now you're multiplying SSR over TSS by n minus 1 over n minus k minus 1. And what happens when you add one additional regressor? It increases k by 1, which means that the denominator actually decreases. And since denominator decreases, the whole term increases. And since we are subtracting a larger number, adjusted R-square actually declines. Remember, we also said that whenever you add a regressor, SSR decreases. So if SSR decreases, this whole term also decreases. And since we're subtracting smaller number from 1, there's a push for r squared to be larger. So adjusted r squared is basically balancing between two opposing forces whenever you add a regressor. And doing that actually, in a way, helps you to avoid adding as many random variables as possible, because every time you add a variable, you get penalized in our adjusted r squared. When you look at the term of adjusted r squared, you notice that n minus 1 over n minus k minus 1 is always greater than 1. And that's because you're subtracting more from n in denominator. So your numerator always is going to be larger than the denominator, and this whole term is always going to be larger than 1. What this means is that our adjusted r squared would always be smaller or equal to r squared. But if n is large enough, then n minus 1 and n minus k minus 1 becomes almost the same. So your adjusted r squared and r squared also becomes almost the same. Also notice that because this n minus 1 over n minus k minus 1 is greater than 1, if this gets big enough, you can have an adjusted r squared that's actually negative. So the good thing about adjusted r squared is that it allows you to compare the quality of fit with different numbers of independent variables. So with r squared, if you have one regressor versus model with the two regressors, then model with two regressor would always have a higher r squared. But with the adjusted r squared, if you have model with, say, one regressor versus two regressors, because the adjusted r squared always penalizes you and tries to balance out if it's good or bad to add another regressor, you can actually compare these two models and say which one is better by looking at the adjusted r squared. There are two different ways of calculating adjusted r squared in Stata. So one way is to just run a regression without the comma robust. So the reason why we did comma robust is because we wanted to adjust the standard error for potential heteroscedasticity. And if you don't want to care about the standard error, if you just care about the adjusted r squared, then we can just run the regular regression model and it would output the adjusted r squared. The second way is using the robust standard error. So we run the regression like we did before. So regress the model and use comma r to get robust standard error. But this only gives you r squared and not adjusted r squared. So after you have an output, you need to enter this command, return list r squared underscore a, and then this should output the adjusted r squared. Here's a model which we have been examining. So we have a simple linear regression model and multiple linear regression model. The r squared shows that multiple linear regression model seems to be a better fit because in simple linear regression model, r squared is 0.05, and multiple linear regression model, we have r squared of 0.426. So this means that in simple linear regression model, only 5% of test score variation is explained by regression model, whereas in the multiple linear regression model, almost 50% of the variation in test score is explained by the model. If you look at the SCR of multiple linear regression is smaller, which means that the y is closer to the regression line in the multiple linear regression than in simple linear regression model. So another thing that you notice is that the r squared and adjusted r squared are very similar in values. And this is because in our case, remember our sample size was 420. So in our case, the sample size is large enough that r squared becomes similar to adjusted r squared. So what's the main lesson here? Adjusted R-square seems to be a better measure of fit than R-square. R-square would always increase whenever you add a regressor, but adjusted R-square doesn't necessarily increase when you add a regressor. So adjusted R-square allows you to compare the measure of fit, or how good the model is fitting the data, across different models with different numbers of regressors. So what should he do then when we're trying to model something? Should he pick something that maximizes the adjusted R-square? The answer is no. The reason is when you're doing a prediction and you try to maximize the adjusted R-square, this may actually lead to poor out-of-sample prediction. So when you maximize adjusted R-square only using the sample that you have on hand, and then you need to predict something using an observation that is not in your sample, this may do a poor job of predicting your outcome that you're interested in. When it comes to causal inference, and you're trying to measure if a variable X is affecting a dependent variable Y, your decision to whether to include another regressor or not shouldn't be purely based on increasing adjusted R-square. The decision to add a variable of regressor or not should be based on whether it's helping you estimate the effect of a causal effect of interest. So in short, when you're modeling something and deciding how many regressors or which regressors to include in the model, it shouldn't be purely based on increasing or maximizing the adjusted R-square.